Product metrics. Now, this is one of the most important aspects in software engineering, and of course, in any other science or technology, metrics plays an important role. If you can measure, you can ascertain or talk about quality. So, how can we measure software? How can we measure the software features? How can we measure the functionalities, the implicit, the explicit functionalities? Various things are there that we are going to see in product metrics. This is McCall's triangle of quality. We have already seen this. The quality of product operation, product revision, and product transition. All these operation, revision, and transition, they have certain quality factors. These are the quality factors which we have already discussed. Now, the McCall quality factors were proposed in early 1970s, but they are still valid today as they were at that time. So it's likely that software built to conform to these factors will exhibit high quality well into today's century. So even if there are dramatic or multifold or proliferated changes in technology, so we need to understand the measures, the matrix, and indicators. What do we mean exactly when we say measure or matrix? Why we are not saying measure only? Why we are talking about matrix or say indicators? So measure, it provides a quantitative. Everything will be quantitative, right? So measure provides a quantitative indication of the extent, the amount, the dimension, the capacity, or the size of some attribute of a product or a process. So it is a qualitative indication of any of these things, right from extent, amount, dimension, capacity, or size of certain attribute of a product or process. So not about the product, we're talking about the attribute or a property or the characteristic of a product. In IEEE, metric has been defined like this: a quantitative measure of the degree to which a system, component, or process possesses a given attribute. Means, what is the quantity or quantity measure of the degree to which this attribute are present in your software. You can understand like this. So an indicator now is a metric or a combination of metrics. You can have one metric, two metrics, combined metrics that provide insight into the software process, the software project, or the product itself. Measurement process. First we formulate, then collect, analyze, interpret, and feedback. Means the derivation of software measures and metrics which are appropriate for the representation of the software that is being considered in the formulation. The mechanism used to accumulate data required to derive the formulated metrics is collection. And the computation of metrics and the application of mathematical tools is the analysis. And the evaluation of these metrics result in an effort to gain insight into the quality of the representation is interpretation. And the recommendations derived from the interpretation of product metrics transmitted to the software team is the feedback. So metrics have certain attributes: simple and computable, empirically and intuitively persuasive, consistent and objective, consistent in its use of units and dimensions, programming language independent, and effective mechanism for quality feedback. Simple and computable means it should be relatively easy to learn how to derive this metric, and its computation should not demand inordinate or indefinite effort or time. Empirically and intuitively persuasive means the metric should satisfy engineer's intuition, what he may think about the product attribute under consideration. Consistent and objective means the metric should always yield results which are unambiguous. Consistent in its use of units and dimensions means the mathematical computation of the metric should use measures that do not lead to bizarre combination of units. And the independency from programming language means metrics should be based on analysis model, design model, or the structure of the program itself. And the effective mechanism of quality feedback, that is, the metric should provide a software engineer or us with an information that can lead to a higher quality and product. So what are the metrics which are related to the requirements model? Function-based metrics and specification metrics. That is, we use the function point FP as the normalization factor as a measure of the size of the specification. or the specification metric, which is used as an indication of quality by measuring number of requirement by type. In the FP, or function based metric, which was proposed by Albrecht, this can be used effectively as a means for measuring the functionality delivered by the system. So function point metric is essentially based on the functionality which is delivered by the system. So function points are derived using certain empirical relationship which are based on direct countable measures of software information domain, and also the assessment of the software quality or complexity. So the information domain value which are required or which are defined in the function based or function point metric. First is the number of external inputs, the number of external outputs, the number of external inquiries, the number of internal logical files, and the number of external interface files. So external input, external output, external inquiries, internal logical files, and external interface files. All these are important as far as function point metrics are concerned. In this, if you want to compute the function points, what we're going to do is, this is our information domain value. We assign the numbers, how many external inputs are there, how many interface files are there. So we assign a number, and then we multiply them with the weighting factor. Means if you say that the external input in our case is simple, multiply this value with simple. If we say no, my internal logic files are very important and very complex, so I'll multiply this value with 15 and get the result. Then I'll count all these. So function point, how we can compute the function point? This total, this is a count total, into these are empirical value, 0.65 plus 0.01 plus sigma of fi. We'll see what this fi is. These are the functions. So we right now we are interested in the count total, and this will give us the direct metric which are called as the function points. What is this fi? I just told you that I'm going to tell you about fi. So these are the value adjustment factor based on responses of the questions. So there are certain questions, like 14 questions, which are being presented by Dr. Pressman in his book. Let me go back again to what we are discussing. We want to find out the function point metric. In this, we are interested in these 5 information domain values. We will give the count number, we'll multiply it with whichever is possible. Means if you say this is simple, I will multiply with this. If you say now, average inquiries, this information domain value is average for me, I'll multiply it with 4. Or I say, no, my external interface files is really important, really complex also. I'll multiply this value with 10. And the value will be written here. I'll count them, means I'll take the addition, and I'll keep it here. Once I keep it here, I know that we have an empirical relationship of 0.65 plus 0.01 into sigma fi. So what this is, fi is sigma fi. Count total is known to us. Now we can find the function point. Sigma fi, these are value adjustment factor, or VAF. That means we need to answer these questions, and then each of these questions is answered using the scale ranges from 0 to 5. 0 means not important, and 5 means absolutely essential. So the constant values in the equation, as you saw, and the weighting factors that are applied to information domain counts, they are determined empirically. So we just have to use the formula because everything is empirical. So what are the questions which are being asked in value adjustment factors? Does the system require reliable backup and recovery? Are specialized data communication required to transfer information to and from the application? Are these distributed processing function? Is performance important or critical? Will the system run in existing heavily utilized operational environment? Does the system require online data entry? Does the online data entry require the input transaction to be built over multiple screens or operation? Are the ILFs we have seen updated online? Are the input-output files and inquiries complex? Is the internal processing complex? Is the code designed to be reusable? Are the conversion and installation included in this design? Is the system designed for multiple installation in different organizations? Or is the application designed to facilitate change and ease of use by the user? So these are the 14 questions we need to answer, and depending upon how important it is or how not important it is, we're going to give the value, like I'll give 0 to this, 1 to this, 2 to this, 0 to this, 5 to this, like this. So I have to give the values, and then we have to add sigma. All these are F1 to F15. I will F1 to F14, I guess, yes. And I'll add these. sigma files, and once I add it, I'll go back. As I have computed already the count total, I'll place it here, and now my function point is with me. So how many function or functionality which are delivered with the system are going to be delivered with the system is our function point. Then we come to the matrix for specification quality. Specification quality means architectural design matrix like the structural complexity. What is the fan out? The data complexity. What are the input and output variables, and also the fan out. The system complexity, the structural and data complexity. So all these are functions of these values. These are our architecture design matrix. We have HK matrix. What does it mean? The architectural complexity as a function of fan in and fan out. Fan in and fan out means if this is, say, a module or some certain function. Fan in means how many modules call this module, or how many modules invoke this module. This is fan in. And then how many modules this particular module invoke, or how many module does this module calls. This is the fan out. This is fan in, this is fan out. Then the morphology metric. This is the function of number of modules and the number of interfaces between the modules. So number of modules and the interface. This is morphology matrix. So we assume that there are, say, NR requirements in the specification, such that NR is NF plus NF. What this mean is the NR requirement is the sum of functional requirements and non-functional requirements. Functional are the exact functionality which are required. Non-functional requirements are like performance, easy to use, usability, maintainability. All are these non-functional requirements. And to determine the specific, that is a lack of ambiguity of requirements, Davis suggested a metric that is based on the consistency of reviewers' interpretation of each requirement, that is Q1 is equal to NUI by NR. NR we have computed just now. NUI is the number of requirement for which all reviewers have identical interpretation. And the closer the value Q is to 1, the lower is the ambiguity of the specification. So the completeness of the function requirement can be determined by computing the ratio like NU by NI into NS. NU is the number of unique function requirement. NI is the number of inputs or stimulus defined or implied by the specification. NS is the number of states which are satisfied. Now this ratio measures the percentage of necessary functions that have been specified for a function, but it does not address the non-functional requirement. So to incorporate these into an overall metric for completeness, we must consider the degree to which the requirement have been validated. So this is Q3, NC by NC plus NV. NC is nothing but the number of requirements that have been validated as correct. And NV is the number of requirements that have not yet been validated. This is Q3. Because we are all also interested in object-oriented design. So what are the metrics of our object-oriented design? Whitmire describes 9 distinct and measurable characteristics of an object-oriented design. The size, the complexity, the coupling, the sufficiency, the completeness, the cohesion, the primitiveness, the similarity, and the volatility. These are the different distinct and measurable characteristics of an object-oriented design. So we are interested in computing the metric of a design. We have just seen about the requirements. Now we are interested in design. So the size. Size is defined in terms of four views: the population, the volume, the length, and the functionality. The complexity. Because in object-oriented we are dealing with the classes and the objects. So how classes of an object-oriented design, they are interrelated to one another. The coupling. The physical connection between the elements of the object-oriented design. The coupling. And the sufficiency. The degree to which an abstraction processes the feature required to it, or the degree to which a design component possesses feature in its abstraction from the point of view of the current application. Completeness. This is an indirect implication about the degree to which the abstraction or design component can be reused. Completeness. Cohesion. The degree to which all operations working together to achieve a single well-defined purpose. Primitiveness. This is applied to both operations and classes. The degree to which an operation is actually atomic. Similarity, the degree to which two or more classes are similar in terms of their structure, function, behavior, or purpose. The volatility, the measures of likelihood that a change is going to occur. So the distinguishing characteristics, Berard argues that these are characteristics which are required that special object-oriented metrics needs to be developed. That is, in object-oriented, we have localization, the encapsulation, the information hiding, the inheritance, the abstraction. So the class-oriented matrix, which was proposed by Chidambaram and Kammerer, they came to a conclusion that we want WMC, weighted methods per class, depth of inheritance tree, DIT, number of children, coupling between object classes, response from a class, lack of cohesion in method. So coupling, cohesion, response, DIT, WMC, a number of children. Class-oriented metrics by Chidambaram and Kammerer should contain, or it contains all these, right? Then the class-oriented metrics were also proposed by Lawrence and Kidd. They said that the class size, the number of operations overridden by a subclass, number of operations added by the subclass, and also the specialization index should be included. Mood also gave some matrix suite in class-oriented metric. He said the method inheritance factor, the coupling factor, and the polymorphism factor is important. So in terms of Lawrence and Kidd, they propose that the average operation size, the operation complexity, and the average number of parameters per operations are important. The component level design metrics. It is very interested in the cohesion, coupling, and complexity. Cohesion is a function of data objects and the locus of their definition. This how well the module or the function they are doing exactly the work which they are supposed to do. The coupling matrix is a function of input and output matrix, the global variables and the modules which are called. The complexity matrix, there are hundreds have been produced. The best one and the most popular one is the psychometric complexity. Then the web app, the design metric for web app, web application, design metric for web app. Does the user interface promote usability? Are the aesthetics of the web app appropriate for the application domain and pleasing to the user? Is the content designed in a manner that imparts the most information about the least effort? Is the navigation efficient and straightforward? Has the web app architecture been designed to accommodate the special goals and objective of web application user? The structure of content and functionality and the flow of navigation required to use the structure or system effectively? And are the components designed in a manner that reduces the procedural complexity and enhances the correctness, reliability, and the performance? So the interface metrics for web app. These are the interface measures like the layout appropriateness, layout complexity, layout region complexity, recognition time, typing effort, mouse click effort, selection complexity, content acquisition time, memory load. So all of these are the interface measures or interface metrics. The aesthetic metrics, how things are seen. So by nature, aesthetic design relies on the qualitative judgment now, and it's not generally amenable to measurements and metrics, but still, Ivory and her colleagues proposed a set of measures that may be useful in assessing the impact of aesthetic design. It can be the word count, it can be body text percentage, it can be emphasized body text percentage. It can be text positioning count, it can be text cluster count, link count, page size, graphic percentage, graphic count, color count, and font count. Then the content metrics. The metrics in this category focus on the content complexity now, or on the clusters of objects together that are organized into pages. So page weight, page complexity, graphic complexity, audio complexity, video complexity, animation complexity, scanned image complexity. Navigation metrics. Metrics in this category address the complex or complexity of navigation flow. So in general, they are applicable only for static web page. We don't include dynamically generated link of pages like page link complexity, connectivity, and connectivity density. So the code matrix, we have Halstead software science. Halstead, this is a comprehensive collection of metrics which are all predicted on the number. We are talking about the count and occurrence of the operators and the operands. Please understand, Halstead means operator and operands within a component or a program. So it should be noted that the Halstead laws, they have certain controversies, but some may believe that they have flaws. But experimental verification of selected programming languages have been performed using Halstead. Now we'll learn about the Halstead theory of software science, which was proposed, as the first analytical laws for computer software. So Halstead assigned quantitative laws to the development of computer software using set of primitive measures that may be derived after code is generated and estimated once design is complete. So after design is complete, it can be estimated, and after the code is done, it can be computed. N1 is the number of distinct operators that appear in a program. N2 is the number of distinct operands in the program. Capital N1 is the total number of operator occurrences. Capital N2 is the number of total operand occurrences. So Halstead uses these primitives measure to develop expressions for the overall program length. So what he gives us: program length, potential minimum volume for an algorithm, the actual volume, that is number of bits required to specify a program, the program level, that is the measure of software complexity, the language level, that is the constant for a given language, and various other features such as development effort, the development time, and even the projected number of falls in the software. So he said, we have seen that what is N1, N small n capital N. So he shows that the length can be estimated by N1 log N2, N2 log N2, N2 log N2. And the program volume can be computed by N, capital N, log N1 plus N2. So it should be noted that this V will vary with the programming language and represent the volume of information in bits required to specify a program. And theoretically, the minimum volume must exist for a particular algorithm. So Halstead defined it as a volume ratio. This volume ratio as the ratio of volume of most compact form of program to the volume of the actual program. So in actuality, L must be less than 1. So in terms of primitive measures, the volume ratio he expressed like this: 2 by N1 into N2 by capital N2. And Halstead work is available to experimental verification, and a large body of research has been conducted to investigate software science. And there is a kind of discussion which is always going on with Halstead, but you must know it. The metrics for testing effort can also be estimated using metrics derived from Halstead measures. The binder suggests a broad way of design metrics that have a direct influence on the testability of an object-oriented system. He said LCOM, lack of cohesion method; PAP, percent public and protected; PAD, public access to data member; NOR, number of root classes; FIN, fan-in, and number of children, and depth of inheritance tree. Now we come to the maintenance metrics. So IEEE, it suggests as SMI, Software Maturity Index, that provides an indication to the stability of the software product, which is based on the changes that occur for each release of the product. So we have the information like this: MT, FC, FA, FD. FD is the number of modules in current release. FC is the number of modules in current release that have been changed. FA is the number of modules in current release that have been added. These are changed, these are added, and these are the number of modules in current release. The FD is the number of modules from the preceding release that were deleted in the current release. So IEEE suggested that the software maturity index can be computed like this: MT, this number of modules in current release, minus FA plus FC plus FD divided by MT. So when SMI, software maintenance or software maturity index, it approaches 1, the product begins to stabilize. This was about product metrics. Thank you so much.